Hello everyone, so it's been a while since we last covered a new video, so today we move on with chapter 11, going over series with positive terms. So this is highly related to the previous section 11.3 in which we went over the telescoping series and the geometric series. So well, what is the relationship between those two sections? Well, we are going to determine whether a given series converges or diverges. Okay, so but what did we do in the previous section that we are not going to do from here on? In this section, we are only going to determine whether a given series converges or diverges, but we're not going to find the value of the infinite sum as we did for the aforementioned series that are in the form of telescoping or the geometric. And we also cover a generalized way to find the infinite sum by coming up with sequences of finite sums or partial sums. However, that work for very specific type of series. The problem is when it comes to that, not every single series is possible to come up with such a sequence of partial sums. So in this case, in this section, that's why we are only going to determine whether a series converges or diverges, right? Which is what we investigate. However, we are no longer going to care about what the value is for the sum. We're going to look at different types of tests, but first we are going to look for the easiest test, the test for divergence. Okay, so there is two things. Number one, given a sequence, we look at the general term and find the limit as it goes to infinity. Okay, if the limit is not zero, or the DNE, then the series diverges. Otherwise, be careful. If the limit is zero, then the test is inconclusive. Okay, so in this case, we're not going to determine whether the series converges, just divergence, and then whether it's inconclusive. So let's look at a couple of examples here. Okay, so we have that. We have this to be our a sub n. So we take the limit a sub n, that is to n squared plus 1 divided by 3n squared minus 1 as n approaches infinity. So this is what are we going to do? We are going to factor out the highest power, the numerator and denominator, n squared times 2 plus 2 divided by 1 over 2, not 2, hold on, that should be a 1 over n squared. Then divide that by n squared times 3 minus 1 over n squared. Okay, so let's see. We can divide out this once right here, leaving us with limit as n approaches infinity of the quantity 2 plus 1 over n squared divided by 3 minus 1 over n squared, where in this case these two terms right here will go to 0. That's because if we plug in infinity to the denominator, again keep in mind that when we divide by a huge quantity, that turns into 0. So in this case, the terms that survive are the 2 in the numerator and 3 in the denominator, and as we can tell, this number is not equal to 0, as we can tell from the criteria for this series. Well, this series diverges. So this is enough evidence to say, so the series diverges. Okay, let's look at another example. So in this case, our a sub n is e to the n squared. So let's find the limit of e to the n squared as n approaches infinity. What is going to happen here? E to the infinity to the second power, which in this case is just a huge number, infinity. Otherwise, d and e, there's no limit. The limit does not exist. And according to this criteria, let's go up here. When we get a d and e, the series diverges. So that's enough evidence to just tell whether the series diverges. Okay. All right, let's look at another one and let's see. So this whole term right here will be our a sub n, the nth term. So we are going to take the limit of 5n squared plus 3 under 1 as n approaches infinity and plug in infinity. But look what is going to happen here. So 1 over 5 times infinity to the second power plus 3. Okay, infinity squared is going to be infinity, which times infinity is going to be even more infinity. Add 3 to that, we basically get 1 over infinity, which is 0. In accordance to the criteria for the test, if we get 0, the test is inconclusive and we need to go and look at another test, which we will later. I will show you and then I'll come back to this one. Okay, so test inconclusive. Okay, we're gonna look at the second test, the integral test. Well, so let's suppose that we have a function with the two following conditions. Number one, continuous, positive, and decreasing on the interval 1 to infinity. Okay, so we are going to convert the given sequence into the related f of x and evaluate the improper integral. If the improper integral converges, then the series converges. Otherwise, if the improper integral diverges, then the series diverges. So let's look a couple of examples here. Okay, and a quick remark right here. So when we cover improper integrals, we got a numerical value that was the area under the curve. In this case, that is not necessary. That is not actually the value of the infinite series. So we need to be careful. So all we will be able to say here is that the series converges or diverges, not the value of the series as we may think about it. So it's not. So we need to be aware of that. Okay, so let's look at this this one example. All right, so let's see. So I'm going to relate this a sub n as a corresponding f of x. So this tells me some kind of f of x equals to 1 over x squared. And I'm going to evaluate the improper integral that relates that. So the integral from 1 to infinity of 1 over x squared dx. If you recall changing the notation for improper integrals, we are supposed to evaluate the limit as b approaches infinity of the integral from 1 to b of, in this case, let me write this as x to the negative 2 dx. So evaluate the integral that will give us negative 1 over x, okay, in which it gets evaluated from 1 to b. And I forgot to write down the limit word. Let me erase the equal sign and input it. Okay, so this is equal to limit b approaches infinity of this quantity. So we are going to have, let me pull out the negative sign in front of the limit symbol to avoid too many symbols and too many parentheses, and then b approaches infinity. So I'm going to evaluate this from 1 to b, from 1 over b minus 1 over 1, which will be simply 1. Okay, let me clean this up. Negative limit b approaches infinity, 1 over b minus 1. But look what is going to happen. If I plug in infinity, all I get is a 0 for the first term, leaving us with the negative in front, and 0 minus 1, which will be a positive 1. Okay, so conclusion. The integral converges. Then the series also converges. Okay, so that's what we get in this case. Let's look at another example. So you might want to relate this a sub n as the corresponding f of x equals 1 over x. It's going to be a little bit similar with some twist. You'll see what I'm talking about in a moment. So we are going to have the integral from 1 to infinity of 1 over x dx. Let me write this using limit notation. So limit of b approaches infinity, or as b approaches infinity of the integral from 1 to b. And this is going to be dx over x. When we integrate, we get limit b approaches infinity of ln of x. Okay, ln of x from 1 to b. Okay, so let's simplify this. Let's evaluate the upper limit minus lower limit using the fundamental theorem of calculus. So this will be b minus 1. And what is this going to be? When we plug in infinity, this is going to blow up to infinity. So basically, we are going to have infinity minus 1, which is going to be infinity. Otherwise, this means that the integral diverges. And so the series likewise diverges. Okay, let's look at a third example. So let's relate this to the corresponding function f of x. F of x equals to ln of x divided by x. Notice the lower limit for the sum. The reason why we're not starting this at 1 or at 0 is because the function wouldn't be defined for x equals 0, because the denominator will be 0. And on the other hand, the domain, the ln part of the function, it's not, we would get a 0 in the denominator. So let's just start this this series at 2. Okay, so let's write this as a function, as an integral. So the improper integral from 2 to what is this, infinity. This will be ln of x over x dx. In this case, we need to do a u substitution. U equals ln of x, and du equals to 1 over x dx. In this case, notice how this 1 x dx is the same as this one right here. So that's what it will serve as our du. Of course, we need to replace the limits in terms of u. U of 2 will be ln of 2, and u of infinity, it will be ln of infinity, which is still infinity. Okay, that way we don't have to do a back substitution, but if you want to do it the other way around, that works. So limit b approaches infinity of the integral from ln up to infinity, in which we are going to have actually u du. The integral of u du will be u squared over 2 as b approaches infinity, evaluated from ln of 2 to infinity. Okay, so let me pull these 2 out of the expression as coefficient to avoid the notation to become cumbersome here, and then I'm going to evaluate the upper limit and the lower limit. So what are we going to have? The b approaches oh, by the way, this is supposed to be well, let's just leave it at as infinity. Don't worry, let's actually skip that part. Let me skip the limit symbol. I don't think we need the limit symbol because I actually evaluated the what is this? I actually evaluated the limit, so this will be u squared divided by 2, evaluated from ln of 2 to infinity. So in this case, we're going to have infinity squared over 2 minus ln of 2 quantity squared divided by 2. Notice this is going to win. This is going to be infinity, which means the function, the integral diverges. Which means the series also diverges. All right, let's look at another type of series, a type of series called a P series. Okay, what are the P series? A P series is a series of this form in which we have 1 divided by n raised to a power p. So we are going to determine whether a P series converges or diverges just by looking at the value of P. So if P is a value greater than 1, then the series converges. Otherwise, the series will diverge if the value of P is less than or equal to 1. Okay? So in this case, let's determine whether the series converges or diverges. So highlight the letter P, in this case the power 2. So it is the case in this one that 2 is greater than 1, right? By this criteria then, so let me actually denote it a little bit better. So in this case, P equals to 2, which happens to be greater than 1. Therefore, the series converges. Because 2 is greater than 1, if the number P is greater than 1, then it converges. Okay? Let's look at the next series, and you might want to rewrite this one before you can tell what P is. Notice in this case, it's given in the form of a radical. So I'm going to change this. N equals the 1 to infinity, 1 over n to the 1/2. So I'm going to focus on that 1/2 right here. So in this case, P equals 1/2, which in this case, it happens to be less than or equal to 1. So in this case, the series diverges. Okay, so the series diverges because P is a number less than or equal to 1, which happens to be the number 1/2. All right. Let's look at another example. Okay, let's look at sigma n equals to the infinity of n to the negative 1.001. Okay, let's rewrite this series in the following form. First, n equals 2, and this will be n to the 1.001. Okay, so let's look at the value of p. In this case, p equals 1.001, which happens to be greater than 1, so the series, therefore the series converges rather. And that's all we do. Just compare with the value of p. Letter D, what do we have to do? Well, letter D, we need to play with powers and exponents. So notice we're given this series in weird looking radicals. Let's convert this first to rational exponents, 2/3, 5, n to the 3/4. Okay, I'm going to pull out the 1/5. That is not going to have any influence in the convergence or divergence of the series. But in this case, I'm going to subtract the exponents. And when I do that, I get n equals n to the negative 1/12. I'll let you verify this by subtracting the exponents. And this will be the same as saying 1/5 sigma n equals 1 n to the 1/12 under 1. So in this case, let's identify the value of p. So the value of p is p equals 1/12, which happens to be less than or equal to 1. And in accordance to the test, the series diverges. All right. Okay, so we are going to have a different type of question right here. So we are given a series sigma n equals 1 to infinity of 1 over n to the 3a plus 2. So for what value or values, well, rather values of a does the series converge? Okay, we know that the series converges if p is a number less than 1. But in this case, what is p? P is in the form of 3a plus 2. So 3a plus 2 less than 1. So I'm going to solve this inequality to find all the values of a for which the series will converge. Okay, so let me subtract 2 to both sides to get 3a less than negative 1 and divide both sides by 3 to get a less than negative 1/3. So you can pick any value less than negative 1/3. Whatever value you can choose, whatever value you choose for a within this shaded region will be okay in this case, in a way that the series converges. Okay, if you choose any value like negative 0.111, 0, 1, 2, any value within this interval I'm shading in purple actually, the series will diverge. Okay, so let's see. Let's look at another test, the comparison test. Okay, what are we going to do when it comes to comparing? Okay, so we are going to determine the convergence or divergence of an ugly looking series like the ones that you're looking here in the blue box. Okay, however, we are going to have a look, basically eyeball the series and try to relate it to something that we know. Okay, look at the end behavior of the sequence related, of the form that we have rather. So we are going to compare a given series with a test series, which, by the way, this test series, I did a little typo. This is supposed to be B sub n, not A sub n. It's a new series. Okay, so this is very important. A test series. How are we going to come up with that test series? Okay, let me look at the first example to give you first an idea, an overview of what are we going to do when it comes to doing comparison of series. Okay, so this is what we do. Okay, suppose for this ugly looking series that all these terms and all these terms are not on the series. Ultimately, the behavior of a rational expression like the one we have over here, or polynomial numerator in the denominator, the end behavior is given by their leading terms, the ones that I'm highlighting in green. That is how I'm going to get this test series, this so-called test series. So I'm going to pretend that these terms are not here, and I'm going to come up with the related series. So I'm going to come up with sigma n equals 1 to infinity of n squared over n to the fifth, which happens to be, in simplified form, 1 over n cubed. Okay, so this series is very easy to test by the previous test using the P series. So P equals 3, which is greater than 1. Okay, it's greater than 1, so converges. So this is a convergent P series. I'm going to do the exact same thing over here. I'm going to pretend on the second one that the n plus 4 is not there, and I'm going to focus only on the leading term. So this will become sigma n equals 1 to infinity fifth root of n cubed under 1. Okay, let me write this in rational expression form. That's n to the 3/5 under 1. And in this case, I have a P series with P equals to 3/5, which happens to be less than or equal to 1. And by that criterion, we know this is a divergent P series. Okay, so this is just a preparation for what we're doing on the actual comparison. So, but first, let's look at this last one. Okay, what about this ugly looking series? Okay, something that calls my attention here is the leading terms. We have 3 to the n and 7 to the n. We have exponential terms, which remind me of the geometric series. But this is not exactly a geometric series. The reason why this is not a geometric series per se is because of this 9n minus 3. So what am I going to do? I'm going to pretend that those two terms are not there, and I'm going to come up with some test series. So sigma n equals 1 to infinity of 3 to the n over 7 to the n, which is the same as sigma n equals 1 to infinity of 3/7 to the nth power. And in this case, we have a geometric series with r equals 3 sevens, which is a number less than 1. And by the criterion of the geometric series, if R, that is the common ratio, is a number that is less than 1, then we have a convergent. Not P series, convergent geometric series. Okay, so let's look at the examples on how to use the comparison test, but first let's go over the test. Okay, so we are going to be given a series to test, a sigma a sub n. Okay, our job is to come up with a test series like the ones that we did earlier on the overview. Okay, and we are going to have two different criteria. We are going to set up this inequality a sub n less than or equal b sub n. If this is true, then the original problem, okay, which is a sub n, will converge just the same way as the one that we have for test. In other words, so we are going to come up with a series that is going to denote a tiny number. So we are going to show essentially that tiny is less than something small. You will see what do I mean by showing that tiny is less than small when I go over the examples. Tiny is less than small. Okay. On the other hand, if we analyze the given series, and we can relate it to a series that diverges, then we set up the following inequality. The inequality the other way around. A sub n has to be greater than or equal to b sub n. And in this case, if that is true, if this is true, then our original problem will also diverge. Okay? And in this case, we will be showing that huge is greater than big. I will show you what do I mean by that. Okay? Let's look at one example. Okay. So, let's determine whether each series converges or diverges. Okay? So, we are going to have sigma n equals 1 to infinity of 1 over n squared plus 2. This is our given. This is our a sub n. Okay, this is our a sub n. Okay, I'm going to relate this series to something simpler, let's say, and let me pretend that this plus 2 is not there. Okay, in other words, let me highlight this with purple. It actually turned into something red, but that's what I'm going to pretend it's not there. So this has the behavior of sigma n equals 1 to infinity of 1 over n squared. Okay, let's focus on this series for now. And let's call this our b sub n. This is the test series b sub n. Okay, and we know that this is a convergent P series. How do we know this is a convergent P series? Because P is equal to 2, which is a number that is greater than 1. That's how we know it is a convergent P series. Okay? So, in this case, we are going to do the convergence thing. So in this case, we are going to show that tiny is less than small. In other words, I'm going to try to show that a sub n is less than or equal b sub n, where a sub n is 1 over n squared plus 2. Is it true that this is less than 1 over n squared? Okay, here is where I'm going to show you that tiny is less than small, because look at the denominator of the left-hand side of the inequality. It's n squared plus 2. That plus 2 will make the denominator larger, and ultimately that quantity is going to become smaller. In fact, it's going to be tiny in comparison with this n squared in the denominator. So in this case, it is true that tiny is less than or equal small. And because this is true, then sigma n equals 1 n squared plus 1 under 1 converges. By comparison with 1 over n squared. Sigma n equals 1 over n squared. Okay. Let's look at another example. Another example in which we are going to call this our a sub n. So this is our a sub n, and let's come up with a series testing. Series to test. Okay, so look at this 2 to the n. That 2 to the n reminds me of the geometric series, but the reason why this is not quite a geometric series is because of this 3 in front of that 2 to the n. All right, so I'm going to pretend that 3 is not there. Let me actually cross it just so you can see the series that I'm going to relate this with. Okay, so n equals 1, sigma n equals 1 to infinity, 1 over 2 to the n. Well, how is this a geometric series? Well, this is the same, 1 is the same as 1 to the n, if you will. Okay, which at the same time we can rewrite this as 1/2 quantities to the n power. And in this case, what do we have? This is our b sub n, which is a geometric, by the way, a convergent geometric series. Okay, so we came up with a convergent series. So because we came up with a convergent series, then again we have to show that tiny is less than small. Okay, tiny is less than small. In other words, a sub n less than or equal b sub n, for which a sub n is 3 plus 2 to the n under 1 less than or equal 2 to the n under 1. And in this case, this is true because let's analyze the denominator of the left-hand side. 2 to the n. 2 to the n. The 2 to the n's are there on both sides of the inequality. However, the one on the left-hand side has this additional 3. So adding that 3 will make the denominator bigger, giving us the final quantity a smaller number. And in this case, that quantity is indeed smaller than the one that we have on the right-hand side. So that's why this is true. So our conclusion, therefore, sigma n equals 1 to infinity, 3 plus 2 to the n under 1 converges by comparison with the geometric series 1/2 to the n. Okay. Let's look at another example. Okay, so what do we have here? Sigma n equals 1 to infinity of 1 over square root of n plus 1. I mean minus 1 in this case. So that square root of n, this square root of n right here we could write it down in terms of rational exponent and then look at a P series. However, this is not quite a P series because of this extra minus 1 that for a second I'm going to pretend is not there. So I'm going to come up with a new series. This becomes, I'm not saying this is equal to this, I'm saying with this arrow here, I'm saying this behaves like, or it is related to this sigma n equals 1 to infinity, 1 over the square root of n, which is the same as sigma n equals to 1 to infinity, and to the 1/2 under 1. Okay, so I'm going to look at the power of n. In this case, is 1/2. So p equals 1/2, which happens to be a number less than or equal to 1. And in accordance to the P series, this is a divergent P series. Okay, a divergent P series. Okay, let's recall again that this is our A sub n, and the new series gives us the B sub n. Okay, so notice in this case we're looking at divergence. So let's go up to the table here. So for divergence, we are not going to show that tiny is less than small. In this case, we are going to show that huge is greater. We're going to show that huge is, okay, I'm having trouble here. I'm going to show that huge is greater than big. Okay, huge is greater than big. How are we going to show that? Okay, I'll show you with the example. Okay, so in this case, we have to show that A sub n is greater than or equal B sub n. Okay, so that is our given, and this is our test. So 1 over square root of n minus 1 is greater than or equal to 1 over square root of n. How do we know this is true? Okay, notice in this case both sides of the inequality have the square root of n. But what is this -1 going to do on the denominator? So let's see, this -1 is going to turn the denominator smaller. When the denominator is smaller, we're dividing by a smaller number. Dividing by smaller number gives us a larger number, as opposed to the previous case that if we add a number to the denominator, we divide by larger number, giving us a final answer as a result. So in this case, this is true. So sigma square root of n minus 1 under 1 diverges by comparison with sigma 1 over root of n equals 1 to infinity, n equals 1 to infinity. Okay, and that's how the comparison test works. Like, let's do a few more examples. I have a few on the next page. Okay, all right, letter D. Let's see what is going to happen here. So I have this ugly looking series, but ultimately we look at the leading term. Let me highlight the leading term with green, and let me highlight with purple the additional terms, the ones that for a second we are going to pretend are not there. Okay, so this series is somehow related to the following series. Sigma n equals 1 to infinity of the square root of n cubed under 1, which is the same as sigma n equals 1 to infinity of 1 over n to the 3/2. And this has the looks of a P series, as you can tell, because we have n to some power p. Okay, so in this case, we know p equals 3/2, which is a number greater than 1. So we have a convergent P series. So in this case, for convergence, we show that tiny is less than small. Okay, but first of all, let's denote this as our a sub n, and these are our b sub n. So a sub n must be less than or equal b sub n. So in other words, we're going to have n cubed plus 2n plus 4, everything underneath the radical, all under 1. Is it true that this is less than or equal 1 over square root of n cubed? This is true because of this bunch of terms. This bunch of terms will make the number inside of the radical larger than n cubed. And because we're getting a larger number in the denominator, when we divide by a larger number, we get a smaller. So this is true. So this is smaller than our test. So therefore, sigma square root of n cubed plus 2n plus 4, 1 over that, converges by comparison with sigma square root of n cubed under 1 infinity n equals 1 to infinity n equals 1 to infinity. And this is how we do the comparison. So again, we are comparing with something simpler for which we know its behavior by simpler tests. So we compare the two general rules and we show that the inequality is true. Okay, let's look at letter E. Okay, so let me highlight this 7 to the n and 3 to the n. This ratio of numbers to the nth power remind me of the geometric series. However, this is not quite a geometric series because of this 9n minus 3 in the denominator, that is in addition to that 7 to the n. So I'm going to pretend that 9n minus 3 are not there. So I'm going to compare this sigma n equals 1, 3 to the n, 7 to the n, which equals n equals 1, 3/7 to the nth power. And what do we know about this series? This is a geometric series with r equals 3/7, which is less than 1. And this gives us a convergent geometric series. Okay, let's label this as our a sub n, and this is our b sub n. The test is the b, the a is our given. So because we have the word convergent here, we are going to show that tiny is less than small. Okay, so in other words, a sub n less than or equal b sub n. That is 3 to the n divided by 7n plus 9n minus 3. Is that less than or equal 3n over 7n? Is it true or false? Well, okay, let me cancel these two factors out so it's easier to see. So 7n plus 9n minus 3, 1 over 7 to the n, here everything under 1. Okay, again, notice the 7 to the n appears on both sides of the denominators of the inequality. However, look at these extra terms. These extra terms are going to add numbers to the denominator, making it smaller than just 7 to the n. So in this case, this is true inequality. Therefore, sigma 7 to the n plus 9n minus 3 under 1 converges by comparison with sigma n equals 1 to infinity 3n to the 7n. Okay, let's look at another example. Let's look at the last couple examples. Okay, so this also reminds me of a geometric series because we have 7 to the n over 6 to the n. If we combine them, we would have 7 6 to the nth power. Okay. However, the reason why this is not quite a geometric series is because of this plus 2 in the numerator. So I'm going to come up with something that looks like something it is easy to determine whether this converges or diverges. That is in sigma n equals 1 to infinity of 7 to the n over 6 to the n, which is equal to sigma n equals 1 to infinity of 7 over 6, the whole thing to the n power. Okay, as opposed to the previous example, in this case we have a geometric series, yes, in which r is equal to 7 over 6, which is a number greater than or equal to 1. By that series, we have a divergent geometric series, in which this is our a sub n, and this is our b sub n. So for divergence, we are going to show that huge is greater than big. That is, we still have a sub n on the left, b sub n on the right. However, the inequality sign flips. So that's what we have to show. Okay. So we're going to have 7 to the n plus 2 divided by 6 to the n. Is that equal? Is it true that this is greater than or equal 7 to the n over 6 to the n? This would be easier to see if we cancel out this 6n and the 6n that is on both sides, because we are going to have 7 to the n, 7 to the n plus 2. Is that greater than or equal 7 to the n? Okay, this is true because look at this 7 to the n's. This 7 to the n is right here. It's also there. Okay. However, this plus 2 would make the left-hand side actually, as expected, bigger than the right-hand side. So this inequality is true. Therefore, we show that huge is bigger than big. Sigma 7 to the n plus 2 over 6 to the n diverges by comparison with sigma 7 to the n, 6 to the n. N equals 1 to infinity, n equals 1 to infinity. Okay, let's do the last of them. For the last of them, let's see. All right, this one might be a little bit tricky to come up with a known series. Okay, because we have a combination of ln and a square root of n. Okay, in this case, I'm going to pretend that we don't have the ln of n. In this case, the one that stands out the most to me is the square root of n in the denominator. So I'm going to pretend this ln of n, again, it's not there for a second. And I'm going to come up with the following. Sigma n equals 1 to infinity of square root of n, which is the same as saying, oh, by the way, this is arrow not equal. This is, but in this case, this is equal. And n equals 1, n to the 1/2 under 1. Okay, let me highlight this 1/2. That 1/2 is p. Okay, okay, let's see. Yes, got it. That's p equals 1/2, which is a number less than or equal to 1. Okay, less than or equal to 1. Okay, and that tells us this is a divergent P series. So in this case, let's label our A sub n and B sub n. So we are going to show that A sub n is bigger than B sub n. In other words, we are going to show that huge is greater than big. Okay, so ln of n divided by the square root of n, is that greater than or equal 1 over square root of n? Well, in this case, it's true because, well, notice that if n gets bigger, okay, substitute different values of n. We don't have to do it because we are not going to solve this by exhaustion, just by observation, by comparison. Okay, this numerator will eventually get bigger and bigger and bigger as n increases. However, the numerator on the right-hand side will always remain a 1. And it's not going to be bigger than 1 or smaller than 1. So this inequality will hold true. Okay? This will hold true. So therefore, sigma ln of n over square root of n diverges by comparing comparison with 1 over square root of n equals 1 to infinity. And this is it, guys. Before wrapping up this section, let me go up and give you a few tricks. Let me go back to the box right here. Something I discovered when I was writing the notes. Okay, convergence. How to not forget about the inequalities. What if you make the mistake of flipping the inequalities? Well, so I would like you to observe this. Let me find a good color to highlight. Okay, so for convergence, look at the inequality sign. Do you see the C right here? Less than or equal looks like a C, right? Let me do that again. It looks like a C, okay? On the other hand, for divergence, look at the inequality sign. This looks like a D right here. Okay, do you see the invisible D? This looks like a D for divergence. Okay, that's the trick to relate convergence and divergence and the inequality signs. And now, let me go up to the very first example. So in this case, we got this test inconclusive for letter C on example 1 on page 2. Okay. So because the test was inconclusive, okay, so in this case we need to go over a different test. So in this case I'm going to do comparison test. I'm going to compare this with sigma 1 over n squared. I'm going to pretend that I don't have this 5 as a coefficient and this plus 3. I'm just going to focus on n squared. Okay, so what do we know about this series? So this is a convergent P series. Okay, so in this case we have to show that tiny is less than or equal to small. In other words, 5n squared plus 3 under 1, is that less than or equal 1 over n squared? In this case, this happens to be true. Okay, this happens to be true because look at the denominator. Multiplying n squared by 5 and then adding 3 to that number will make the denominator way big, and a denominator that is way bigger gives us a total quantity of way tinier. So tiny is less than or equal something small. So sigma 5n squared plus 3 under 1 converges by comparison with sigma n squared under 1. Okay, so this is what we are supposed to do when we get a test inconclusive. We have to go and look for a different test. Okay, is that it about the different tests for convergence and divergence? Well, the scope of this course is up to this test only. However, there's more tests. There is a test called the limit comparison test, which is very similar to the comparison test that we just did. We come up with a test series, but then we take a limit. We are not going to do that for this course. There is another test called the alternating series test. Okay, the alternating series test. And then there is another one called the ratio test. And finally, the root test. Okay, so that's about it. That's all. Those 4 tests are not in our textbook, so we don't have to cover this. So just the one that we cover in this section. So this is the end of the section. I will see you on the next video on 11.5. Okay, bye.